Yeah, so great to be here. My name is Anas Abdul Rahim. I am the team lead for AI at Julia Sim, which is a modeling and simulation platform that's tasked with building the next generation of tools to enable the next generation of technology that engineers can bring to our world today. Our talk today is about bringing modern CI/CD machine learning pipelines to Julia and making it more accessible to people in the open source community. You know, from the Julia Sim perspective, we're whether it's trying to build, machine learning models from the Julia Sim, sorry, I should say the Julia Sim AI perspective, whether it's trying to build machine learning models that will accelerate your inference time so that instead of a simulation running on a supercomputer taking, several months, you can try and scale that workflow down to a week within more manageable resources, or trying to discover, missing physics to a particular physical asset that you have in real life, which you have a simulation for, and you also have data for, and you'd like to kind of find the bridge between the two that actually properly represents the behavior of the deployed asset. Building these algorithms themselves require processes that allow you to, that will augment your ability to kind of develop it in a way in which you get outcomes that are expected and tempered and methodological. So the way I want to kind of start this off is through this comic from QCD, and the idea here is that most people, when they first deal with machine learning, the typical kind of exposure to the workflow is you have an API that's provided to you, you have a data set, you have a bunch of hyperparameters, and you kind of just stir the pot, so to speak, and you hope that at the end what you end up getting as a machine learning model is something that will meet the outcome or expectation of the kind of result you were looking for. And the idea here is that, in fact, when you look at machine learning from a production perspective, indeed, there are actual processes that lead to incredible results. Because of the fact that machine learning is a data-driven model process, is a data-driven model, and the actual process of building machine learning is a data-driven process. So every time you build, one version of a model, or I'd like to move away from the word model and move towards pipeline. You get insight on why it failed and what you need to do next in order for you to iterate and build something that's more robust and scales to the actual application here. And the idea here is that it turns out that within the Julia ecosystem, there's actually a very familiar workflow that everyone has actually kind of been exposed to when it comes to package development that you can use now as a robust process to develop pipelines in an iterative fashion that will actually lead you from going on in terms of stirring a pot of hyperparameters and hoping you get something amazing to maybe the next NeurIPS or ICLR publication, which becomes a spotlight hopefully. So the agenda for what we have in store today is we're going to start off first by very briefly discussing what we mean when we say machine learning pipeline in a broad sense. And then from there, we're going to kind of motivate the different kinds of parts of this workflow that we're introducing and why it's required and needed. And then after that, we'll be going into the latter half of the presentation, which Dario will be leading, which will be a demo of the actual workflow that is being proposed and the kind of tools that the open source community can use to help create pipelines in a more robust manner. So, most people here, I'm assuming, are very familiar with, a basic generic machine learning pipeline. But of course, for those who don't know, and just kind of a brief overview, you start off with generating a data set, whether it's collecting one from the internet, whether it's having a simulator and querying it. The next step is to pre-process it, put it in a place in which the machine learning model can deal with more appropriately based on how it's formulated. And then you choose your model architecture, you train the model, you validate it, and you kind of repeat this loop over and over and over again until you converge to something that gives you the results that you want. And obviously the last step is to deploy, and this is part of the kind of the continuous deployment aspect of things from the CI/CD acronym, but this is a part that we won't actually be discussing today. So moving on to like the motivating factors of why it's important to have these kinds of processes when it comes to developing machine learning algorithms. And the first thing that I'd like to motivate here is that machine learning is incredibly hard to debug. And the reason being is because when your code fails, when you run your test or you run something in Julia, you're going to have the REFL barf back at you and tell you exactly what it is just went wrong. And you're going to have the code trace to walk back and go back to that line of code that tells you this is the part in which you made an error for. That doesn't make sense. But when you have a machine learning algorithm, it'll just run and it'll just give you a result. And whether that result is correct or not is completely up to the metric that you have, or in this case, the kind of visual obviousness of this being wrong. So the example on the left here comes from OpenAI, and the source is at the bottom, and it's about faulty reward functions. And the idea here is that you have this video game called Coast Runner, where the task is, it's a race. You try and finish the race, and you try and collect as many points as possible. And so the kind of rational thing is, well, if I design a reward function that's supposed to motivate some kind of behavior for my agent to accomplish the task of finishing the race and collecting as many points as possible, the idea here is, well, if you just create a reward function that says, try and collect as many rewards as possible, then what it ends up doing is it realizes, well, and in that reward function, the game itself doesn't reward you for finishing the game or progressing through the race. It just rewards you when you get points. So if your reward function only rewards you whenever you gain points, then the agent kind of finds this clever solution where if I just do a donut in circles and keep collecting the same point over and over and over again, then I'll never finish the race, but I'll meet the objective of maximizing my reward. So you end up getting the most rewards you can possibly get in the game, but never actually meeting the objective to begin with, which was to actually finish the game from the get-go. And these are the kind of pathological behaviors that kind of come up. And this is just one example. For example, another example could be when you're doing classification, and suddenly, every single image you feed in turns into a cat, and you're just wondering, why is that the actual case? And again, there's no error that was thrown. You did your forward pass, you got an answer, but there's no way to actually debug that process. So. The idea here, and this is really the overall theme that I'd like to kind of bring up here, is that machine learning is software and you should treat it as such. There are very strong design patterns that exist in the software development community that need to be directly applied when it comes to actually building machine learning as well, including pipelines. And the idea that I want to kind of first start off with here is that it is so important to actually treat the development of a machine learning pipeline through the same lens as you would developing software when it comes to the ideas of test-driven development. And of course, many times we'll start off and use a package, and the API of that package has been thoroughly tested. But then when you use it in your own context, in however way you do, there are always subtleties and nuances that comes into play here. An example could be how you normalize, for example, or when you initialize your neural network and its distribution of weights results in activations that saturate and don't let you, train well or whatever it may be. These are all things that you can fundamentally test. And the important thing here is that, as will be shown later, that you can actually structure your machine learning project in a way that it turns into a package, and you can kind of use the testing ecosystem of Julia to actually create this pipeline in a test-driven manner. Should probably put my phone out just in case, just to make sure we're on time here. Okay, cool. In terms of here, these are just examples of the kind of tests that you can do. So if you have a simulator, for example, you can test your actual simulator if you're building one from scratch, or if you're just kind of evolving your system. You can test the distribution of your data, test normalization. There's so many parts of the pipeline that you can test. For example, when you train your model, you can pick a baseline that the model should succeed in order for you to move over for your next step. And these are the kind of tests that you can create along the process before you move on to your real task, in order for you to actually have a pipeline that when you get to the real task itself, you're not losing your hair, so to speak, which I have very little of, to trying to accomplish your goal itself. So this is an example where, as you can see, the way the project is structured, and Dario will be going through this. So I just realized, already 10 minutes in, I'm trying to leave as much time for the demo as possible here. But you can see that the way you structure your packages, you have some kind of template that you're interested in, like a broad generic machine learning pipeline that has, your data generation script, your layer, which here is your actual model, your pre-processing, your actual training algorithm, and then here you can see that in the test set, in your run test file, that you're running all your tests that include each part of the pipeline that you would typically run together, and then only after then you run your actual experiment, the thing you're trying to conduct and get a whole final outcome for that's hopefully useful. And the idea here is that if you follow this mentality of treating package development, of taking the tools of package development itself and applying it to your machine learning project, you get tons of benefits. So one of the key things that is absolutely hair-tearing is the notion of state. So when you're evaluating from a REPL and you're just running a line of code, and you can notice sometimes that suddenly you'll get a different result, and you won't know why. But then you'll realize that maybe 10 line executions ago, you did something that overridden a state inside of yourself, inside of your REPL, which you don't know about. So whenever you kind of instead push all your evaluation of your machine learning experiment / pipeline to the testing environment where you just run tests and it runs all the tests and then it runs your actual experiment, you get a sandbox state. So you don't have a sense of, you don't have to worry about this fact of that you might have some kind of hidden state that you evaluated earlier. It's all fresh. It's basically starting a REPL from the start in some sense. So the next thing I want to get to very quickly here is the idea of reproducibility. And this is such an important part. So this is an example, again, from OpenAI. They always have the cool stuff, which is hide and seek game, where on one side, the whole point is they have to learn to kind of win the game itself, which means they don't get caught by the opposing team. And on one side, you have, they learn to kind of block the passage so they can't get in. But then later on, the agents realize they can take the map, so the ramp, and actually climb in and lose the game. And then there's this other version of it, down the line in your pipeline, where they learn to pull in the ramp first before they block the passageways, and that way they win the actual game. And so this is more illustrative, but the idea here is, suppose you had an algorithm that suddenly made a leap in performance. How the heck did that happen? Right? To be able to kind of track exactly what kind of code state got executed in order to get this kind of performance is very, very important. And so the next thing, of course, that I want to bring up is the idea of using Git in order for you to be able to track the code changes that went into both the development of the tests and also the actual code state and hyperparameters and everything else that went into the experiment that you just run as well. And this gives you a history of what exactly has gone into the experiment so far, and it even gives you the ability to move down the line of comparing different code states so that you can know again, have an understanding of how the project has been developing, what led to what, and getting insights from that as well. Okay, and again, kind of rushing through this to make more time for the demo. The idea of the kind of workflow that you would go through is you write your individual models, you write your tests, and it's exactly like you develop a package. You go back and commit what you need to write for your test itself, and then when you run your actual experiment, you have one final commit that designates that this commit is for the experiment that was run. And then when you look back through your Git history, you'll have a very readable kind of chronological timeline of what exactly went into the experiment up to that point. Okay, and the idea here is that you can go back and look at Git diffs and things like that. So the next thing I want to talk about is that the reason why you also need these kinds of pipelines itself is that machine learning has a lot of knobs to turn, and being able to kind of keep track of, in order for you to explore this entire space, you need a lot of compute, or you need to be able to run things in parallel. And one of the interesting things that you can do, one of the interesting ways of kind of facilitating this is the idea of being able to kind of hook on these runners that can run multiple things in parallel for you, and being able to kind of like scroll through it. And something very familiar for people in the Julia ecosystem is when you finish developing a package and you push your tests, you have a build kite runner that runs all your tests for you. And then we just showed that your experiment, if you kind of hijack this process of test-driven development and using the Julia package ecosystem, you can now push all your experiments in the same direction as you would when you push a test to a repo. So it's the same kind of mentality here. And this will allow you to run multiple things in parallel as well, and being able to kind of explore your space as needed. Now, of course, I'm not suggesting for people to suddenly hijack the open source community CI and start running, machine learning experiments and block everyone's progress with that. I'm just suggesting that, when you create your pipeline, the same way you think about how your package gets developed and run in the Julia ecosystem, you can now hijack these processes for your own use with your own compute. That's probably one thing I want to mention. Okay, and yeah, this is just going through this very quickly about how you can. How it makes it much more easier to take a runner workflow, just like you conveniently think about in your package development, and run multiple runs in parallel, explore them, and then obviously the last piece to all of this is first you start off with a sandbox environment that will run everything and test, then you will commit everything so you can make sure you have a history of what you're doing, and now you want to be able to explore in parallel very quickly, and the final step to all this is being able to keep track of all your explorations. Like I mentioned earlier, the idea of developing a machine learning pipeline is that deep learning models are data-driven algorithms, and the workflow behind making them succeed are data-driven processes. The idea of running an experiment, what happened, why did it fail, working back from that information, iterating forward, and being able to track all those efforts is incredibly important. Now, of course, if you're really into torture, you can go ahead and pull out an Excel sheet, and best of luck. But of course, the most beautiful thing is, again, machine learning of software, treated as such, and one of the strong design patterns when it comes to software development is integration of tools. It's very important to not start from scratch every single time, and having some kind of experiment tracker to collect all your results that you've been working on so far, so you can have some kind of history of what it is exactly that you've done so far. And for example, this is what's called a parallel coordinate plot, where every vertical axis is a parameter that you've done, and if you trace through it, it would be one experiment. So, I used a dimension size of 32, and I used the dropout of this number. And you can kind of track all your experiments to see what ends up giving you the best kind of result. And the idea here is that, again, if you incorporate these kind of experiment trackers into your actual workflow, and then you have this kind of final completed pipeline that'll allow you to develop machine learning algorithms in a way that will not only give you the opportunity to develop something that will be very robust, but at the same time, it'll give you the kind of insight and accelerate your ability of an iterative workflow. Because when it comes to data-driven processes and learning how to actually take your algorithm from something that's failing to something that's giving you state-of-the-art results, there's so much that goes into it, and keeping track of all the details along the way so that you can go back and reflect and do your post-analysis is going to be key here. So now what I'd like to do is kind of hand it over to Daria here, who's going to talk about an example of how in the Julia ecosystem you can use the tools that already exist to create this pipeline and then demonstrate for you actually what that all looks like. So I'd like to hand it over to Daria.
Thank you. So as Anis basically spoke about right now, we used a bunch of tooling to actually come up with a pipeline. And the important thing to note here is that these pieces basically are put together, but they're completely independent of each other. What that basically means is that you can swap each part out independently of what it is that you actually want to do. What we did was we took over the Julia PKG ecosystem, the testing environment, and CI, and then hooked it up all together to basically give us this very extensible pipeline that we can use to run our experiments and pipelines in parallel and keep track of them properly. So now I wanted to go over and show you what an experiment or a pipeline package would look like. So let me make it a little bit bigger. So hopefully this is something very familiar to everyone here, right? So this is basically what a Julia package looks like. We have our source and test directories and everything exactly like we would set up anyway. What is slightly interesting is this lib directory. Now here is where we store something that we call template experiments or template pipelines. What they are basically is something very, very simple that we would want to replicate over multiple of our pipelines and experiments. It has a file structure that we will explore in a minute, and it has existing sort of context and pieces that basically make it easier for the next person who is trying to come up to start with the pipeline directly rather than having to futz around with Julia. But let's now try and see if I can. Is this big enough for everyone? Hopefully.
Is this going to be a public repo? Because right now it's private. Yeah, I mean, it still hasn't been released, but yeah,
it hasn't been released
yet.
yet.
Not yet.
But this.
Yeah, we'll do some touch-ups and yeah, we have an agenda for that.
Right. So I've basically loaded in the same package that you saw earlier, and what I want to do is I want to start with creating a new pipeline using my templates that I have, right? So here is something like we're already familiar with. We are used to forking experiments, right? So we have the template experiment already that we want to basically now use. So all I have to do is call this fork experiment function. It'll start a new project for me. It'll and hopefully also activate the environment. As you can see right now, it's completely empty. So that's cool, right? What that did for us was basically give us a new environment where we can actually implement our pipelines. So I'm going to exit the REPL really quickly, and I'm going to come here and show you a pipeline that I was working on earlier for this demo. Now, again here, as you can see, this is again just a simple Julia package, right? And now let's go and explore some of the other things that we have access to here. All right, let me switch back to our GitHub repo. So this is exactly the same thing, just the same package. And what I want to point out here is specifically the same notion that we saw earlier. ML is software, so we should treat it as such. This is just a package, and with ML, we saw that we have these generic design patterns that come up over and over again. Your basic steps of data generation, of pre-processing, training, visualization, such and so forth, right? So we can see all of those things represented here as well. So let's go into one of these things. We see all of those files right here: data generation, pre-processing, modeling, etc. Okay. Here we have very, very simple functionality that we'll talk about in a minute. But the idea here is that we have these compartmentalized functions which consume some parameters and then output certain output variables that are necessary for our pipeline to basically come together. The same things that we see here in the source are also replicated in test, right? So you have your data generation, your modeling, your pre-processing, and so on. Now, while we are in the test environment, I want to quickly go over to the run test script. As you can see, again, something like we're very, very used to, right? In package development, we have all of our test dependencies, we load all of them, and then we start running our tests. This is something very standard. What we've added on top of it is the idea of an experiment, right? So this is where we will actually be doing our experiment running. So let's now look at what this run experiment script does for us. All right. So we can see what we have here is a workflow function. So this is the function that we will be using to actually execute the pipeline that we intend to track and actually make use of in our downstream tasks. As you can see, again, we see the replication of our steps in order, right? We have our modeling, we have the data generation, pre-processing, training, and so on. Interestingly, also we see that we add a bunch of logging for just logging our metrics as we go along for visualization, and finally we add some visualization to basically wrap up and see how we actually performed overall. So in this case, what we have done is we have taken over or sort of forked or built upon the MLflow client library. So this is an ML ops backend, which we have integrated alongside LabTracker. And its job is basically to help us both log and track all of our experimentation and do post hoc analysis for us. All right. Finally, we just have a run from config function. We will go into the config in a minute, but the idea here is that we should be able to now run all of our experimentation in parallel, as we spoke about. Right. So let's go to the config really quickly. This is a very, very self-explanatory thing, but it's very important for us to note that all the pieces that are required for our pipelines to run are present in there in very very organized manner. So, for example, we start with the port that our logging server is going to run on, something very simple. The module that we are logging, stuff like that. Again, so let's go into the parameters section. We can see here again that the same notion of this hierarchical component and sequential component that we have built is represented here. Again, we have inside our parameters the modeling component, the data set component, the train component, and so on. One interesting thing is that because of the way it is architected, right, it is all going to be hooked through CI, as we spoke about. It means that we can basically use any kind of data source. Anas mentioned using simulators or local files that we're loading, whatever the case may be. We can hook it up to cloud providers if the need arises, and so on and so forth. In fact, all of our compute runners could easily be something that we run locally with the help of CI local runners, or something built on top of cloud providers, depending on the kind of compute infrastructure needs that come up for your problems. Awesome. So with this, what I want to do, I want to run a quick experiment. Let's look at our config script really quickly. The same things that we saw on Git are replicated here, right? Let's say I wanted to add noise to my model and see how that performs. Or rather, let's see if I change the number of batches that come through, right? So let's do that really quickly. Let's say I want 20 batches instead of 10, sure. What we'll do is we'll call the test function like we do in Julia always. So as a package, this will run off all of our tests, and we should basically see the output in just a moment. So what has happened there is our run experiment script is designed such that it comes after all of the PKG tests go through, right? So that means that anytime we see any kind of breakage, it will shout at us if something goes wrong. So we're just going to wait around, right? And this is what we are basically greeted with. As you can see, what has happened here is that it has told us that it has found the ability to run 6 independent runs based on the config that we have, and it is giving us the basic what's it called the URLs to access any one of them. So what we can do is we can go over here, and this will take us to our MLOps backend. Soon enough, this will load. Let's just go to the experiment tab for now. Awesome. So here you can see all the runs that I had run previously. These are basically instantiations of our pipeline over different configurations, parameter structures, so on and so forth. As you can see, we have a very clear view of all the things that we can indeed check for example, any columns that we might want to add. For example, I don't want to see what dataset I was running, but I do want to see the loss that my model is at currently. So this is all happening in real time, right? So any time my model updates, all of these values will get updated. So we can go to one of these previous runs if we want and see what that looks like as well. As you can see, all of the parameters that we ran our configuration with are exactly replicated here. Alongside, we have metrics. So this is a loss metric that I wrote for my training script. And we can see that that plotted in real time as well, hopefully soon. All right, you can see, I mean, sure, this is doing something kind of nonsensical, but the idea here is that we can go into our model and analyze as it's running and even after the fact. As a matter of fact, what we can do again is we can go back to our experiment tab and we can compare across runs. Right, so we get this parallel coordinate plot again. Running over multiple experiments, we can basically see how exactly our progress has been, what caused our models to perform well, and what caused them to perform not so well. I'm a little bit short on time, so I will try to be a little bit quick here. But the idea here is, again, let's just go to one of our runs. We can see that what we have here is our commit URL. Well, let's go and see what happens here, right? It takes us directly to our GitHub repo that we were playing with in the first place. So we can see what actually caused the change in our model output, right? So in this case, we can see that we changed the width and height of the model that we were running with, and we changed the detection threshold that it operates with. This way, what we have basically done is we've come full circle, right? We started with a commit. That commit was replicated on Git, which then comes up on our MLflow backend, where we can actually do any kind of analysis and comparative work comparative study that we're interested in.
Yeah. So that we're a little short on time here. We're trying to leave some time for questions. We were hoping a little more time for questions, but that puts us at the end of our presentation. And I think we'll open it up for questions. I know
Let's thank the speakers. Yes.
Thank you so much. That is super awesome, and I was totally trying to set something like this up myself, and it's not super easy. So I would love if there's as much as possible to kind of copy from this, especially also with respect to if you need like GPU devices. Obviously, you don't get them so easily from GitHub. How to kind of set up your own GPU devices. I saw that I guess you have their own cluster and how to hook that up.
Mm-hmm.
One question I have is, does it mean now that every time I push new Git commits, it kind of reruns all the experiments I have, even if they may be expensive and takes like an hour or something?
So that's a very good point, and I can actually demonstrate that here really quickly. So say I wanted to actually change my experiment. I want to do something interesting with it, right? So, hello?
I think you're just going to have to illustrate the point.
Yep, seems like the REPL is dead. Let's say I wanted to change something in my config, and I rerun the experiments, and what that will do is it will spawn more runners, obviously. Now, this is CI, so we can choose what we want to happen here. We can have it fail fast for us, and because this is test driven, and we know that our tests are going to run before our experiments, if there is anything indeed that is wrong with the setup in our experiments, it will error before it ever reaches a point of ever submitting an experiment. What that means is that our CI and our experimentation queue and the analysis area, that our MLOps platform is not really going to get runs that are never going to complete. Or in the odd chance that it does, we can obviously clean up. But we have taken mitigation precautions to make sure that that we just don't get to that stage where we have to come back and clean those runs up.
Yeah, thanks for the talk. What is the connection, comparison, differences with Dr. Watson? Because that's one of the main packages that exist in the Julia ecosystem for this.
So Dr. Watson is obviously a very great platform, right? It allows us to orchestrate a lot of these similar what do you call pipeline pieces. What is different here is that we're able to basically, rather than having to track things manually via Git, what we are doing in this case is that we're offloading that work from the user to the experimentation queue. This way, we are not making manual Git changes, but we're letting it decide for us. As you saw in the commit messages, we're letting it basically figure out where those commits will end up, what experiments they're going to go with, and any other binary dependencies that those experiments have. So while Dr. Watson is really, really good for experimentation setup, and I recommend it, this is just a simpler way of making sure that the pipelining pieces are offloaded as much as it can be from sort of manual configuration and more to the compute.
Thank you very much for the speakers, and thank you